So you're new to vacuum tubes and you want to know what a vacuum tube does. Well, you come to the right place. Now this is going to be a very, light overview video of what a vacuum tube does, not really in depth. So if you're looking at, how do I hook this up in a circuit? This is not the video for you. So anyway, without any further ado, I will cut to the chase. Now, to understand what a vacuum tube does, I'm going to have to shut that light off. You'll see, what is the simplest form of a vacuum tube? Well, this is. Now, I don't know how well you can see it, with the light off, but this is a reproduction of an early tungsten filament light bulb. So, current goes in through the base, up around the filament, which is a resistor, and that glows, right? This would be called, strictly speaking, a monode, meaning one contact, but it's really not considered a vacuum tube, so we don't call it that. Anyway, so this filament gets really, really hot and it emits a light, but it also emits a lot of electrons from there. And that's due to an effect called thermionic emission. Now, so I can explain the rest of this, I'm going to screw this back in. But before we talk about the vacuum tube circuitry, I bet most of you know what this is. This is a diode, right? This happens to be a germanium diode from the 1940s. And this, if you're watching this video, I assume you know what a diode is. It'll allow current to go one direction, but not the other. So we can actually do this using a vacuum tube. So you can ignore the rest of this for now. This is a diode vacuum tube. So whenever you see these parentheses or like a circle, that just means that is the glass envelope or the metal envelope of the tube. And whenever you see like these cathedral peak things or like a sort of half moon looking thing, that is the heater filament. And yes, heater filament, that is just like a light bulb. So basically a diode is a light bulb through which we run some current. It's usually around 6.3 volts, although that can go anywhere from like 1 volt to several hundred volts depending on the tube. But for simplicity's sake, we're just going to call it 6 volts here. Anyway, so this is heated up to glowing white hot, and it's giving off all these electrons. And these electrons go from, in the vacuum envelope now, from the filament, they race up to this, what we call the plate. So this is called the filament, and this is called the plate. So the electrons are all zooming in this direction. So that allows current to flow this way. However, if the current tries to flow this way, the electrons try to flow this way, since this plate is not heated, the electrons can't fly in the other direction. So that means the electrons can only flow here and not here, creating a diode. See? Pretty simple to understand. So this is, cool and all, but it's not tremendously useful. So in the turn of the century, Lee de Forest, a gentleman named Lee de Forest, invented what he called the Audion tube, which is the first triode. Now, I have some vintage triodes here. These are from 1924. They are both UV201A tubes, and these are both vacuum triodes. This one is more representative of what you found back then, where it has this metallic look that is metallic barium, the element barium, that has been flashed onto the inside of the glass, and that helps to scavenge the last oxygen from when they make the vacuum. But anyway, I'll set this one aside and look at this one because this one's clear. This is an example of this tube here. It's a directly heated triode. And we'll get back to this in a second once you know how this works, but just know this exists. Anyway, so this, if you take this out, right, looks just like the diode. You have the filament and you have the plate. But now we're introducing a new part. This is called the grid, right? It's labeled CG here for control grid because there's, foreshadowing. Anyway, what this does is when you apply a potential to the control grid, instead of the electrons zooming straight from the filament to the plate, they actually get hung up on this control grid, and that interrupts the flow. So it is sort of a NOT gate, if you will, right? If you know logic. So this you might be thinking, wait a second, that sounds familiar. And yes, you're correct. This is the predecessor to the modern transistor, except it's opposite because, it's inverted. But this is used for amplification. I should mention, the diode here is used for rectification, demodulation of RF signals into audio signals, anything you'd use a diode for, like this type of diode as well. Anyway, the triodes here are used for amplification, also sometimes for rectification and demodulation, stuff that you could do with a transistor nowadays, right? So this is called a direct heat triode because the cathode, right, is directly heated. The cathode is actually the filament. Now I have a cutaway here I drew of this very tube, and you'll notice, see this inverted V part here? That is our filament, and that glows white hot, right? And you can't really see it because it's thinner than a human hair, and it's suspended in the middle of this tube here, and I know for a fact you cannot see it. But concentric around that are all these wires that are a bit thicker, and that's our control grid, right? And then this solid piece of metal out here, that's our plate. So being as our cathode is directly heated, this thing is glowing white hot. This looks like a light bulb inside of the radio. And all these early direct heat cathode tubes, they all look like that. They look like light bulbs. So later on, we get an indirectly heated cathode. Now you can see there's still the heater filament, but then we have this other plate over here, and that has the negative potential. And this just allows a little bit more efficiency in the operation of this tube. Point of note here, I have these labeled high voltage, but that's only a relative term. I mean higher voltage than the filament is usually operating at. That can be as low as, 5 volts or 24 volts, 300 volts, 3 kilovolts. It could be a whole bunch of different things, but that just means that it's higher than the filament voltage. I digress. You'll see that this is electrically identical to the directly heated one. It's just, since we are running this at a lower temperature, this is orange, it's no longer white, it's heating this cathode, and the electrons are still going through and still being arrested by the control grid. All hunky-dory. If you add one more electrical element to that, you'll notice di, 2, tri, 3, tet, 4. So tetrode, or tetra, I should say, not tet. Tetrode, 4. 1, 2, 3, 4. Look at that. So it looks just like this triode here, the indirectly heated triode. All these, by the way, are drawn as indirectly heated because those are more common nowadays, but nowadays. Anyway, you'll see we have another grid here, and it's labeled SG. This is what we call our screen grid. So, to explain what that does, you have to understand that you'll see we have a plate here and we have a plate here. This is essentially just a giant capacitor, right? And there is a bunch of capacitance behind this. And that is really not good electrically when we're talking certain frequencies. So in order to interrupt this capacitance, we add another grid in here. And now this grid, you'll see, is a little bit sparser than the control grid. In this, you can see the control grid is really tightly packed. It's a really dense thing. The screen grid is a little bit looser than that, just a little bit. And what that does is it lowers the capacitance between these two terminals here and improves the response of the tube. So you don't really see tetrodes as often as the other varieties, but know that they do exist. Next up, we have 2, 3, 4, 5. Pent, 5. 1, 2, 3, 4, 5. Cool. So this looks, yep, just like the tetrode, except, what do you know, we've added another grid here. And it's the suppressor grid. Now, when you're running at higher frequencies, let's say the megahertz, or back then megacycles range, you would get the electrons going from negative to positive, but then they rebound back. They rebound off that plate, and that's not very good. That introduces some resonance in the circuit, and that will really just kind of mess up whatever you're trying to do, especially in a radio. So what we do is we add this suppressor grid. You'll notice it's a lot more sparse than even the screen grid, right? Which is still here, the screen grid, right? Control grid, screen grid, suppressor grid. But that just, if an electron goes back, it is just going to be absorbed by that. The suppressor grid is usually externally tied, can be internally tied to the negative side here. So that is sometimes connected. And that does the same thing. It's essentially just controlling, again, the flow of electrons from negative to positive. Same thing that we're doing all the way back in this simple one. So we're going to skip number 6, because those are really uncommon, and go straight to 7, hept, right? 7. 1, 2, 3, 4, 5, 6, 7. Would you look at that? Now, these are also called a pentagrid converter, right? Because if you look at how many grids, 1, 2, 3, 4, 5, we have 5 grids. Now, that looks like a whole bunch of stuff going on. It's really not, trust me. This is essentially, if you take a look, CG, SG, CG, SG, and suppressor, right? That looks a lot like a pentode. And remember, the pentode's not really that far off from a triode. This is just a pentode and another pentode in the same trench coat, right? So this requires that both these control grids have no potential on them so that the electrons go and flow in a straight path, right? If either one is on, it prevents the flow. And this is basically a simple NAND gate, right? If you know logic. So this is a really powerful thing to have, right? In one tube, right? These heptodes are usually found in superheterodyne circuits in, let's say, the 30s and 40s, in the internal oscillator circuitry for creating the frequency that they mix to get the intermediate frequency, if you know how a superhet works. But these are also often found in televisions from the 50s. And again, it looks like a whole bunch of stuff, but it's really not, right? Vacuum tubes are really simple. I think I glossed over, but the pentodes and tetrodes are also used in similar circumstances as triodes, just depending on the frequency we're dealing with, right? So instead of a tube like this, which comes from a radio that can only do medium wave, which is the AM broadcast band as well as the 160 meter band in ham radio world. And then when you get, later tubes from the 40s that look like this, you get more pentodes because those are operating in the megahertz or megacycles range, and you're trying to reduce those resonations. Resonant, whatever. It's 4 a.m. and I can't speak English. Anyway, that also goes for audio amplifier technology. Since audio, we can't really hear above a few thousand hertz. Really, a pentode is really, really overkill. So generally speaking, you use triodes because they sound nicer. They have a softer response. So you could actually use this fine in a audio amplifier, provided you could find one. These are kind of rare and expensive now. And tubes come from, this is a medium-sized tube. They make miniature ones, but they come from miniature size all the way up to these giant tubes here. This is a broadcast tube, thank you, Ron, from a local transmitter. This is an IMAC 5500A, but despite it being absolutely chonker, it's still just a pentode. So it's electrically like this, except this one, when it's powered up, this will singe your hand off and make you wish you've never been born. Anyway, there are other variants of vacuum tubes that are not here, obviously. There's double diodes that are used as like 2 diodes in one envelope. Those are used for full wave rectifiers. There's double triodes. There's also different types of junk. This is a 6G5 tube from the 1940s. It's called a tuning eye. This is essentially just a miniaturized cathode ray tube, and this is used as sort of a primitive VU meter for tuning superheterodyne radios of the era. But like I said, I won't teach you how to hook these up in a circuit, but if you've seen from my previous videos, courtesy of the Radio Museum online, I have some schematics here. This is a Freshman Masterpiece radio from 1924. And this is a tuned radio frequency set. You'll notice this actually uses these exact tubes. I pulled these tubes out of my Freshman Masterpiece radio. But you'll see, there's not much to it once you take out the heater voltage. It's just straight current going through. It's not much here. And then even from the same year, 1924, you have the famous RCA Radiola AR812 superheterodyne radio. Now this looks like a whole bunch of spaghetti, but again, you take off half of this stuff here. Admittedly, this is not the neatest schematic in the world, but if you take off half this stuff here for the filaments, there's not a lot going on here. Vacuum tubes are a lot more intuitive, in my opinion, than modern circuitry, despite the fact that you need to, power them with the heater voltage. I think I'll leave it at that for now. Like I said, this is only supposed to be a very cursory introduction to vacuum tubes. So if you have any questions, just post them in the comments, and I don't know how to end this. Bye!